Hello everyone. Welcome to the Global NCG seminar. Today we are very glad to have Paolo Piazza from Sapienza University di Roma, and he will talk about surgery sequences, higher invariants of Dirac operators. Let us welcome.
Okay, so first of all, thank you for the invitation. It's a pleasure and an honor to talk in this seminar, which has really a lot of success. And today, as you can see, I want to talk about some joint work with Thomas Schick and Vito Felice Zenobi. So let me start right away. I will start with kind of a gentle introduction with the idea that maybe there are graduate students, so I apologize for the experts, but it will be rather short, but in any case, I hope interesting for everybody. So, how do I do that? I don't know what's happening here. Oh, here we are, yeah. Very good. So this is the outline of my talk. I will start with the Higgs-on-Row surgery sequence. I will talk about K-theory invariants. I will talk about numeric invariants, in particular higher row numbers. I will give some details, and then I will talk about some geometric applications. So I'd like to say that today, but this is was not planned at all. There is also a talk by Thomas Schick on the same topic, 5 o'clock. So you can have a full immersion in this topic today. So let me start with the Galois gamma covering of a smooth compact manifold without boundary M, and we consider a Dirac operator acting on the sections of a vector bundle, and d tilde will be the lift, and d tilde is a gamma equivariant operator, of course, and what we are interested in are K-theory invariants associated to these two operators. And this is one of the themes of this talk, a way of extracting numbers out of these invariants, these K-theory invariants. So we also want geometric applications of all these, okay? So this is our goal today. And so one way to organize these K-theory invariants is by using the Higgs-on-Row analytic surgery sequence. So this allows to recover some known invariants, like the fundamental class in Kasparov K-homology, or for example, the index class, but also to define a new invariant, which is the row class of an invertible operator. Okay. So let me say quickly what is the Higgs-on-Row surgery sequence. So, well, here it is. This is the Higgs-on-Row surgery sequence. I have to tell you who are these algebras, but there is a short exact sequence of sister algebras, and the Higgs-on-Row analytic surgery sequence is just the K-theory sequence, the long exact sequence associated with it. Okay. Now, who are these algebras? So D star is the non-closure of a certain algebra, which is the algebra of operators which are of finite propagation and pseudolocal. Pseudolocal means that the commutator with the compactly supported function is compact. Whereas C star is defined in a similar way, but you require the operators to be locally compact. Locally compact means that if you simply multiply T by F, compactly supported function, then you get a compact operator. And this is C star is an ideal in the star, and therefore you get that short exact sequence. Okay. So feel free to interrupt and ask questions. Other questions? Okay.
Will there be some nice example of such a sequence, concrete, given manifold covering and so on?
You mean specific or?
Yeah.
Well, as you will see, I mean, this star is a kind of difficult algebra, but C star is just the row algebra of M tilde. So we know that rather well. And for example, is the C star algebra associated to the groupoid M tilde cross gamma M tilde, just to, if you know better that kind of algebras. I mean, so this is the answer to your question. I mean, D star is somewhat difficult to write down, but C star is just the row algebra.
Okay, thank you.
Yeah. So, for example, let me point out, because this will be important later, that this is the pseudo-differential operator of compact gamma support are a subalgebra of C star, okay? And the zeroth order operators are a subalgebra of D star, okay? Even of D star C. Right? And this remark will play a role in this talk, okay? Another point is that there is a non-trivial isomorphism, which is called the Paschke duality isomorphism, which gives you the isomorphism of the quotient algebra with the K-homology of M. This is a very important piece of information. Another piece of information is what I was explaining to Piotr, namely the row algebra is just the C star algebra of that groupoid. And we know from general theory that that is just the K theory of the C star algebra of the group. Okay, so this relates two terms in the sequence with known K theory groups. Now the third term, namely the K theory of D star, is the analytic structure set. Okay, and this is a more mysterious term, but also a very interesting one. So here is the Higson row sequence in a known after this isomorphism. Okay, I have rewritten it using the isomorphisms that I just explained. Now let me explain how to get K theory invariants out of Dirac operators. And so one way, which you find already in the book by Higson and Rowe, is to fix a chopping function, so namely a node function converging to plus and minus 1 for x going to plus or minus infinity. And then we take the functional calculus associated to d tilde. And of course, chi square minus 1 is going to 0 at infinity. And this means that chi of d tilde is an involution in the quotient. That means that that operator, 1/2 1 plus chi d tilde, is a projection. And so if that is a projection, we get a K theory class in the quotient. Okay. So if we are in even dimension, then we use the grading in order to get a K1 class, a true involution. And one can show that these classes correspond to Kasparov classes under the Paschke duality isomorphism. So we have recovered something that we already know, but in a different way. And now in the long exact sequence, if you take the connecting homomorphism and you apply it to this class, you get what it's called the coarse index class. Now, it is an interesting exercise to show that the coarse index class is in fact the usual one given by the Kohn-Skandalis projector, or if you like Mishenko-Fomenko better, this is also the Mishenko-Fomenko class, which is given in terms of finitely generated projective modules over the sister algebra. Okay, so it's actually an interesting exercise to show that all these definitions are compatible. Okay, so but these are known classes. Now let's talk about this new class. Okay, so let me assume that d tilde is L2 invertible. Okay, if it is L2 invertible, there is a gap at 0, and if I choose this chopping function in the right way, then that operator chi of d tilde with chi a chopping function, I can make it just the sign operator. Okay. This is just a preliminary observation. Now, of course, if d tilde is L2 invertible, then the index class will be equal to 0. Index class measures exactly the abstraction to a perturbation to make the operator invertible. So if the operator is invertible, certainly the index class is 0. And the row class, therefore, is a natural lift of the fundamental class. So here the situation is the following. You have the fundamental class in the K-theory of the quotient. The boundary homomorphism sends this class to 0 because the operator is invertible. And therefore, you can choose a lift. In fact, it's a natural lift. I can show you this lift is the following. So as I said, you can simply take the sign function instead of chi, d tilde, and your row class is just this class, okay, this class. Now, this class is the row class, so let me summarize what we have done so far. So in the Hickson row sequence, we have recovered the fundamental class, the index class of d tilde, the lifted operator, and we have this new class, the row class in this group, this analytic surgery group. Okay. So are there questions on this? So this is the summary of what I've done so far. 3 fundamental invariants. Questions? Okay. So let me go on. So one example is the following. Just take a positive scalar curvature on M. By Lichnerovich, we know that the spin Dirac operator is invertible. And so we can define the row class of this positive scalar curvature metric to be just the row class of this invertible operator. This is one of the main sources of row classes. Another one is the following. Take 2 oriented manifolds and orientation preserving homotopy equivalents, and take the union of these 2 manifolds. Then we know that the signature operator on the covering of M can be perturbed to be invertible. Okay, this is famous work of Hilzum and Skandalis. And so now we have a perturbation which is invertible, but you can still define the row class in the same way. And so you have the row class of an homotopy equivalence. So this is another important source of row classes. So let me say that there are different treatments of the Hickson row surgery sequence. So one is due to Xie and Yu, and this employs Yu's localization algebra. Another one is an approach by Delay and Goffeng, which described the surgery sequence a la Baum-Douglas. So instead, for example, instead of the analytic K-homology, they use the geometric model of K-homology, and the other terms are also described in a similar way. Finally, there is an approach using groupoids due to Zenobi, using the adiabatic groupoid, and this is actually rather important for this talk. Okay, so far I talked about these three classes, and I've given you two fundamental examples on how the row class, a row class can arise: positive scalar curvature metrics and homotopy equivalences. Okay, now why we call this surgery, this K-theory sequence, the analytic surgery sequence? So the reason is the following. I will be very short here. Namely, in the original papers, because there are three of them, by Hickson and Rowe, they proved that the Browder-Novikov-Sullivan-Wall surgery sequence in topology can be mapped to their sequence, the Hickson-Rowe sequence. Okay, so there are three papers explaining this, and let me say that the fundamental point is the possibility of defining the row class of an homotopy equivalence. Okay. Now later, with Thomas Schick, we proved that similarly, the Stolz surgery sequence for positive scalar curvature can be mapped to the Hickson-Rowe surgery sequence. Okay, by that I mean that this is a sequence of groups, and you can map this sequence of groups to the Hickson-Rowe sequence with commutative squares. Okay. Once again, the fundamental step is the row class of a positive scalar curvature metric. Okay. Let me say that these two results were treated and generalized and treated in different ways in several papers. So I will talk about Xi and Yu, which use the other description of the analytic surgery sequence. Zeidler also, this is for the Stolz sequence. Myself with Thomas, we gave a different treatment of Hickson-Rowe for the signature operator. Zenobi and also Weinberger, Xi and Yu, in a very long paper, gave very interesting contributions. The last two papers, in fact, are valid also in the topological context. And in particular, this last paper of Weinberger, Xi and Yu is very interesting because the row class of an homotopy equivalence is proved to have an additivity property that is very, very subtle. Okay, so by the way, this is a very robust theory because you can also, for example, show with Albin, we showed that the Browder-Quinn surgery sequence for Witt pseudomanifold, so this is something in intersection homology and all that, can be also mapped to the Hickson-Rowe sequence. So the Hickson-Rowe sequence is really the target of many interesting mappings from geometry to analysis. But of course, to talk about this would take, you know, every item is a different talk in a way. Okay, so let me go on now. Questions or remarks or comments? I don't know. Okay. So Now, remember that what I wanted to talk about was how to extract numbers out of these K-theory classes. And so let me talk about a fundamental work of Alain Kohn and Henri Moscovici. Here, I'll make a little variation on the original treatment. So, as I said, we want to extract numbers. And so for the index class, there is a seminal work by Kohn and Moscovici. I think many of us read their paper very carefully. It's one of the fundamental purposes in the subject. And so let me assume to fix notation that M is even dimensional. And let me fix a group cocycle phi. Okay. Then we can define a cyclic cocycle in the following way. So here is the definition, you can read it. And this turns out to be a cyclic cocycle and defines an element in the cyclic homology of the group algebra of gamma. Now, let me point out that this cyclic homology class is in the cyclic homology localized at identity element. And namely, the definition is the one in the 2 lines before this last item. That's the definition of the cocycles, which are localized at identity element. Namely, they are 0 if the product of the elements is different from the identity. Okay. Let me remind you, or let me tell you, that the cyclic homology of C gamma, in fact, is the direct product of the cyclic homology localized at the conjugacy classes, where the definition is as before, only that now the cocycle is 0 if the product does not belong to the conjugacy class. Okay. In fact, a famous theorem of Burgelia tells you exactly who are these constituents of this direct product. Okay. This is actually very important in applications. And so, as I said, this is explicitly computable as a matter of fact. Now, Kohn and Moscovici defines a smooth, namely a dense, holomorphically closed subalgebra of the Caesar algebra of gamma, the reduced Caesar algebra. And this you can do for any gamma, any finitely generated gamma. I mean, you don't need any additional hypothesis here. Now, you can take the non-commutative Diaramology of this algebra. I'll say more about this in a moment. But the important point is that you can also take a Chen character. So this was defined, for example, in a little book by Karoubi, but you do that in a kind of, you mimic the usual definition with characteristic classes a la Chen-Weil. And you can define this Chen character. Now, it's known that the non-commutative Diaramology is a subgroup of cyclic homology. In fact, you can say exactly what it is. And so you have this pairing, okay? You have this pairing. Now, in general, however, that cyclic cocycle that I defined before will not extend to this algebra, okay? So there is an extension problem. And what Kohn and Moscovici show in their famous paper is that if gamma is Gromov hyperbolic, then there is a representative cocycle such that the cyclic cocycle extends. So this defines now an element in the cyclic homology of B gamma. And this means that we can define these higher indices now, because the Chen character brings you to non-commutative Diaramology. Non-commutative Diaramology is in cyclic homology. This cocycle extends, cyclic cocycle extends, and you can pair. Okay, and of course, let me say that this is not the only content of their paper, because they also give a formula for this pairing, famous higher index formula. Okay, but in any case, we were able to define these numbers now. So, are there questions so far?
Yeah, sorry. Can you recall us maybe what is the non-commutative Diaramology?
I'll get to that in 3 slides. Okay, I have a slide where I explain it rather carefully.
Okay, thanks.
So it's planned. As I said, more on this later. I'll tell you in a moment. Other questions or comments? Okay, so anyway, these are the higher indices. Okay, but now we would like to define the higher row numbers. Okay, so this is our goal. After all, we want to extract numbers out of the row class. So what is the roadmap? The roadmap is the following. What we will do, in fact, is we will map the entire Higgs row sequence to a sequence in non-commutative Diaramology, okay, with commutative squares. And then, in analogy with what I just explained, we will pair with the cyclic homology of C gamma under additional assumptions. Okay. So this is the program. So these results are contained in this paper with Thomas Schick and Vito Felice Zenobi. Let me point out that there is a new version of this paper where we have added a lot of geometric applications. And I should also mention that there is another paper on the subject by Chen, Wang, Xie, and Yu. Jianmin Wang, not Heng Wang. There are many Wang. So this is especially the definition of higher row numbers is also contained in this paper. But I should add maybe that the common results are really obtained by different methods. So in my opinion, the two papers complement each other's. Okay, questions, comments? Now let's get down to business, and let me answer to one question that we had before, namely how you define non-commutative Diaramology. So if you have a unital algebra, non-unital, you can proceed by unitalization. You can consider the universal differential graded algebra and the quotient with the graded commutators. I use this notation. AB means abelianization. And so this is this defined. Oh, let me say first of all that if A is a Frechet algebra, then you want to take the projective tensor product, and then you would take the quotient by the closure of the commutator, but this is a more topological definition. This, of course, defines so this abelianization of the universal differential graded algebra is a complex, and so you can define the cohomology of that complex, and that is the non-commutative Diaramology. In particular, you have the non-commutative Diaramology of the group algebra, or for that matter, of any smooth subalgebra of the sister algebra. Okay. So this is the definition of, so basically the first line gives you the definition of the non-commutative Dirac homology. Let me say right away that in fact, you can define these groups for any differential graded algebra over A. That means that omega 0 is equal to A, but then omega dot can be anything, but must be a differential graded algebra. This actually will be important for us, this remark that I just made. Now,
sorry, Paolo, just a silly question.
yeah.
If you take for your A some usual algebra, so smooth functions and some compact manifold, will you recover the usual Dirac homology or complex?
Yeah, of course, yes.
Okay.
That's so this is very well explained in a little book by Karoubi, which is called Homology Clique, Homologie des Dirac Non-Commutative, something like that. It's an asterisk little book where I mean, the LaTeX is very old, but the mathematics is very clear, in fact. Yeah.
Okay.
And yeah. So as I was saying, you have a basis for the non-commutative forms over C gamma, and you have an inclusion. You have an inclusion of this complex into the complex of any smooth subalgebra of the C-star algebra. Okay. So, for example, this could be the subalgebra of Kohn-Moscovici, but in fact, any dense holomorphically closed subalgebra would do. Now, in the complex of non-commutative differential forms, you can take the forms which are concentrated at the identity element, namely, you have this condition. And you can take the closure of these inside the complex for the Frechet algebra, okay? And this is, by definition, basically, by definition, this is the non-commutative Dirac homology of A gamma localized at the identity element, okay? Of course, you can also take the quotient complex, and you also get the delocalized non-commutative Dirac homology. Now, as usual in these topics, you have a long exact sequence that you can read on the slide with a connecting homomorphism. And so this will be the target of our map. So let me remind you that we started with the Higgs-on-Row surgery sequence, which I rewrite for you. And one of our main results is the following theorem. Given any smooth subalgebra of the C-star algebra, we can define Chen character homomorphisms, which make this diagram commute, okay? So in particular, as you can see, you can map the row class. If you take the central group, you can map the row class to the delocalized non-commutative Dirac homology of A gamma. So this square in the index is just the group made periodic. So this is the main theorem, and it corresponds to the first step I explained in the Kohn-Moscovici approach, the variation of the Kohn-Moscovici approach, namely you map the index class to non-commutative Dirac homology, and then you pair. Now we are in the first step. We first map the whole surgery sequence to non-commutative Dirac homology. Then we will, busy ourselves with the problem of pairing. Okay. Now let me say, so this is one of the central results in our paper. Now, the way we prove this theorem is by using a different realization of the surgery sequence, which employs pseudo-differential operators throughout. Okay, so in other words, you pass to much smaller algebras, and this concreteness allows you to prove the existence of these Chen characters. In fact, I will explain in a moment how you do it. So let me explain this point. This is maybe the only point that I want to explain. And to fix ideas, M is odd dimensional.
Sorry, Paolo.
Yeah.
Because it was so important, could you please go back to the previous slide?
Yeah.
You see, could you explain this superscript? So HE I understand. So this is this localization at the neutral element of a group. And then this DEL, what it stands for?
This I explained it in the previous slide. So let me go back for you.
Sorry, I forgot.
No problem. So you see, you look at these last two lines.
Last two lines, yes.
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 Yes. So you take the image of the one which are localized at identity, and then you take the quotient of all of omega A gamma by disclosure. These are the delocalized forms on forms on A gamma, and you take the homology of this complex.
How to understand when you have no superscript in this sequence?
Sorry?
If you go back to this slide with commuting squares, please.
So here is delocalized, and
yeah, that's where I've got it. Thank you. Yes, and you also have one H without any superscript.
No, that's just non-commutative Dirac homology as I defined it in the beginning of the previous slides.
But you mean without this condition of things being localized at the neutral element?
No, this is just the homology of the universal differential graded algebra in the topological setting with the projective tensor products.
And very naively thinking, so when you have your Chen character from K-theory, why do you choose to land in this non-commutative Dirac homology instead of cyclic homology?
You will see it why, because you will see it in a moment. I will explain it exactly why you want to get to that.
Okay.
Or more precisely, why naturally you get to that. Okay. I will explain it right now. Yeah.
Great.
So, as I said, let me fix M odd dimensional. And so my goal now is to explain this map, the delocalized Chen character. So let me take the sister closure of the operators of 0 degree with the gamma compass support. So this is my notation for them. And it follows from this Zenobi realization of the surgery sequence that there is a surjection from the K-theory of this Caesar algebra to the analytic structure group, this S1 gamma, and the kernel is this K-theory group. So it's the K-theory group of the continuous function on M. So this map brings the projection onto the positive part of the spectrum on d tilde, which is well known to be an element in this algebra, into the row class we are interested in. Okay, so this means that the kernel will pair trivially with delocalized cyclic cocycles. And for this reason, let me concentrate on defining this map instead of the other map. Okay, so I'm going to solve for you a slightly different problem, which is easier to explain. Okay, in other words, I want to explain how you go from the K-theory of the 0th order pseudo-differential operators to the delocalized non-commutative Dirac homology of A gamma. Okay, so this is my goal in the next 2 slides. And the way you do that is the following. So first of all, let me forget about topology and let me define an easier map, which is I go from compactly supported pseudo-differential operators to the delocalized homology of C gamma, not of the algebra A gamma, which is bigger. Okay, so this is a simplified problem. So our approach builds on work of Alencon, Lott, Nister, and Golokowski-Lott. So let me start. Let me take this infinity functions on M tilde. Really, I'm taking the sections of a bundle, but let me forget about the bundle for the sake of simplicity. So this is a C gamma module, and this is my notation for it. I can also consider the Mishenko bundle over M, defined by M tilde. This is very well known and widely used. And it's known, it's used in many circumstances, that there is an isomorphism of C gamma module between C infinity C M tilde and this Mishenko picture, simply associating to a function or a section, because there is a bundle there that I'm not writing, this sum. You translate with the right action. Okay, very good. Now, the adjoint action of this isomorphism identifies the pseudo-differential operators with gamma compass support with a certain subalgebra of the Mishenko-Fomenko pseudo-differential operators. Okay, so this is a smaller algebra. Okay, so the elements of this smaller algebra are, in analogy with what I said before, are just obtained by translating with the right action pseudo-differential operators on M tilde. Okay, very well. And of course, we can also take the tensor product of the Mishenko bundle with the non-commutative differential forms on C gamma, and we have this E omega star C gamma. Okay. Now we can take the endomorphism of these E omega star C gamma commuting with the natural action of the non-commutative forms over C gamma. And inside this space, we have an extension of the zeroth order pseudo-differential operator. So an element in this space is obtained in the following way: is simply obtained as before by translation, and then you have these basis elements in omega star C gamma. Okay, so this is a typical element in this space. So it has these coefficients, pseudo-differential operators, translated by lambda, and then you have these purely non-commutative things. Okay. Okay, so now Lott defined a connection going from the basic C gamma module, E C gamma, to E omega and C gamma. And this has a curvature, which is an element inside here. Now you can define a degree 1 derivation on the pseudo-differential operators simply by taking the commutator with this Lott connection. And of course, this derivation has not square equal to 0. Okay, so it's not, you haven't got a complex, but you can say exactly who is the square of this D bar, nabla bar. I wrote it here. And now there is a trick by Alencon in order to turn this triple, namely psi 0 omega star, the derivation and its curvature, to a differential graded algebra, okay? And we call it omega bar, okay? So this you find in the finitely generated projective case in the book of Kohn, for example. But here we have extended it a little bit, okay? And these are ideas that come from a paper by Gorokowski-Lott. Okay, so now there is a Chen character, a very general Chen character that you can define. And, sorry. And there is also a delocalized trace, which I defined for you here, okay, associated to a zeroth order pseudo-differential operator with the differential form coefficients. And for example, if you take just a pseudo-differential operators without the differential forms, this delocalized trace would be just this element here. Okay.
And what is it you integrate over? What is this script?
This is a fundamental domain. Fundamental domain for the action of on M tilde, yeah, on the covering.
Yeah.
Okay. So this induces a chain map from this algebra, this differential graded algebra over the pseudo-differential operators over the zero to what we are interested in defining the delocalized non-commutative Dirac homology of C gamma. Okay. So of course here there are things to check, but the upshot of this is that you can compose these two maps, and this allows you to pass from the K-theory of the zeroth order pseudo-differential operators to the delocalized non-commutative Dirac homology of C gamma. And here is the last line of, sorry, the last line is the summary of what I just defined, okay? So now this is the way I wanted to explain how you pass from the K-theory of the zeroth order pseudo-differential operators, where your row class is, to non-commutative Dirac homology, okay, of C gamma. So this is the map that I was trying to explain. In general, there is an isomorphism of the structure set with a mapping cone algebra. And so you have to work a little bit more to do the general case. But what I explained here, this last line here, is basically, so let me go back, sorry, let me go back to what we were trying to explain. We were trying to explain this map here. We were trying to explain this map here, okay? And now we managed to map this map, okay? How we did it is but through this construction that I just explained with pseudo-differential operators. Okay, so now we are here. We have our row class, and so we can take this delocalized Chen character, and we end in the delocalized non-commutative Dirac homology here. Okay. Now we know that non-commutative Dirac homology embeds in cyclic homology. And so now we would like to pair this class, this Chen character of the row class, we would like to pair it with cyclic cocycles localized at the element X, okay? Because as I said, we ended up in the delocalized part of non-commutative Dirac homology. So this is an extension problem similar to the extension problem in the paper by Kohn and Moscovici that I explained before, okay? And in other words, you cannot not always do that. And so what we would like to do is, given an element here, we would like to extend it to a class in the cyclic cohomology of this algebra, A gamma, of a smooth algebra, and then we would pair and get a number, okay? Now, this would make sense of this delocalized Shen character of the row class with the non-commutative, with this class, this delocalized class, okay? So in order to do that, as in the fundamental paper by Kohn and Moscovici, you have to assume that gamma is Gromov hyperbolic. I mean, it's very, or polynomial growth, but anyway, it's very unclear how to do it in general. And so let me try to explain this point. So let me say right away that this is a difficult problem already for the delocalized trace. If you want to extend the delocalized trace, this is already a difficult problem. Recall that in the paper, as I explained before, in the paper of Kohn and Moscovici, the group cocycle was localized at the cyclic cocycle was localized at the identity element. Here we are in the delocalized case, and so it's a more delicate matter to extend. Already for the trace, this is a non-trivial problem, and it was solved in a very original way by Mikhail Pushnik in a paper where he defined a very specific smooth subalgebra in the case in which gamma is Gromov hyperbolic, such that the delocalized trace associated to conjugacy class extends, okay? Now we extend this result with Thomas Schick and Vito Felice Zenobi. And so here is our result. So if you are in the Gromov hyperbolic case, then there is a first result where the Hochschild cohomology localized at X and the cyclic cohomology localized at this conjugacy class can be described in terms of polynomial growth cocycles. This is a first result. This is a first result. Then there is a even more delicate result, namely that the cyclic cochains of polynomial growth extends to the Pushnik algebra and define an injection of the cyclic cohomology localized at this conjugacy class in the cyclic cohomology of this Pushnik algebra. This is a particular algebra that is defined in this paper by Pushnik, okay? So let me say that we build heavily on work of other people. So for the first result, we build heavily on the classic paper by Burgelia and a paper by Ralph Meyer on combable groups. And the second result builds very much on the paper by Pushnik. Okay, so this is if you want, it's an extension of the result of Kohn and Moscovici to conjugacy classes which are different from the identity element. Okay, and as I said, this is delicate matter, and it's really built on work also of other people. Okay, so now let me summarize what we have. So for an hyperbolic group, Gromov hyperbolic group, not in general, we have a pairing between the cyclic cohomology localized at the conjugacy class X with this part of the Hickson row surgery sequence. the elements in S star and tilde. Namely, how do we do it? We take the delocalized chain character that I explained before, and then we pair. Okay, the delocalized chain character lands in cyclic homology, or non-commutative Dirac homology, and then you can pair. Okay, this is the fundamental step. Now, if I take X equal to the row class of a Dirac, of an invertible Dirac operator, I can finally define the higher row numbers. And these higher row numbers now are defined for any element in this group. And for example, I can take a positive scalar curvature metric, and I can take the Dirac operator associated to it. We know by Lichnerovich that is indeed invertible, and then we can define the row class of this metric. And more on higher row numbers. So there is another pairing that we can define, which is the pairing with the relative homology. This also with the assumption that gamma is Gromov hyperbolic. And notice that this pairing was also defined by different means by Weinberger, Xi, and Yu. Okay, so they do it using the bound cone isomorphism. We do it proceeding in a similar way to Kohn and Moscovici, very similar to Kohn and Moscovici. So only that they do it for smoothing operators, we do it for zeroth order pseudo differential operators, but it's very similar. Okay. So you can employ these two pairings to define higher row numbers, for example, higher row numbers associated to positive scalar curvature metrics. So the first pairing is useful in the presence of torsion elements in gamma. So this pairing, the first line. The second pairing, you don't need torsion elements, so it also applies to torsion-free groups. So that's an interesting point. And well, let me say maybe very quickly, because my time is over, 2 minutes, that we apply these to very specific problems with higher row numbers. So we take the concordance classes of positive scalar curvature metrics. So we know that once we fix a base metric, this as a group structure. And we can consider the co-invariants associated to a finite index subgroup of the diffeomorphism group. And we know that there is a surjection from the pi zero of that quotient to the concordance classes. And so now we want to measure the rank of this group, the co-invariants associated to a subgroup of the diffeomorphism group. And here is a first result, which is just a small generalization of a result of Xi and Yu. So the rank of this group is bounded below by this element, this cardinality. So these are the element of finite order or the element of finite order which are not conjugate to the inverse. Okay, so this gives you very strong result on the rank of that group. Okay, in particular, that rank will be greater than 1.
What is the meaning of the n?
N is the dimension of the manifold. Sorry,
okay.
I should have said yes. Okay, so this is this sharpens just a bit result of Xi and Yu, but I should say that their result is more general. Another result, and I stop here, comes from old paper by Baum and Kohn. So we consider F gamma. This is just the maps of finite support on the elements of finite order. And here is a result which sharpens the previous result, namely, assume gamma is Gromov hyperbolic, and assume that the automorphism group of gamma is finite. This is not a strong assumption. Then there exists a finite index subgroup of the diffeomorphism group of M, such that you can bound from below the rank of the co-invariants of positive scalar curvature metrics in this way. Okay, and I mean, this you can write down. I mean, this you have constituents of these groups that you can write, and so you have a lower bound for the rank, which is rather explicit. So this generalizes the previous result. So my time is over, and I think I really have to stop now. And I thank you all very much for your attention.
Thank you very much for the very nice talk. Do we have any comments or questions from the audience?
Yes, I have one small question, because I did not follow the work of Pushnik. So what is the distinction between his algebra and the Schwarz algebra that we had constructed with Henri? I mean,
so his algebra is defined in terms of a quasi-derivation delta, which goes basically from C gamma to a certain tensor product of C gamma with itself. Or
I see. But you mean it's known that it's not the same as the Schwarz algebra?
No, it's not the same.
It's not the same.
It's a smaller algebra.
But it is stable under holomorphic calculus, I guess.
It is stable under holomorphic functional calculus, indeed. Yes, it's so if you want, it uses very much the hyperbolic assumption.
Yes.
And it's a smaller algebra. It's a smaller algebra.
It is smaller, yes, of course. It has to be smaller, yes, yeah.
It's a smaller
So
algebra. It's a very interesting work.
Yeah.
And we use it very heavily, in fact.
Sure.
Yeah.
Yeah, one key difference is
Yes.
for the Pushnik algebra, all the other cyclic cycle also extends.
Yes.
And like the part coming from the delocalized part.
I see. Yes.
So
yeah,
I think
this is the fundamental difference with the one you use with Henri in your paper in topology. Yeah. It's a very interesting algebra, I must say.
Yeah, I mean, it's quite interesting that it's defined in terms of a derivation, as you say. I mean, because that's a general.
It's a quasi-derivation. It's a quasi-derivation. It's not a
quasi-derivation.
But
sure.
but it's yeah.
You mean it's a derivation with values in a bimodule, or what? Or
it's no, it's not a real derivation. It's a map to the tensor product of a certain algebra with itself somehow.
Okay. Yeah, but what is the rule of quasi-derivation then? I mean,
well, I mean, it's. I guess you have a less than equal than instead of equal, or something like that. Yeah.
Okay. Okay. Anyway, yes, that's quite interesting. Yes. Yeah. I have another general question, which I already discussed with Yolang. I mean, somehow, with cyclic homology, you have higher invariants which pair with algebraic K-theory. And I wonder to which extent, this can be used in this framework.
You mean with algebraic K-theory?
Yeah. You see, for instance, there is these two parallel long exact sequences which relate the relative algebraic K-theory, the algebraic K-theory, the topological K-theory. And underneath, you have a corresponding sequence in cyclic homology and Hochschild and the operator S. And there are regulator maps which relate the two. So I was wondering, You know, this is a joint work we did
yeah.
with Karoubi. I mean, long
Yeah,
time ago.
well, no, I wouldn't know how to answer to that question. I mean, maybe something like this non-commutative analytic torsion that.
Well, it's related. Yeah, it's related. It is very much the same spirit. Yes.
Yeah, I don't know. I don't know the answer to that question, but it's a very good question. Yeah, it might be related to this work of John Lott on the non-commutative analytic torsion. Yes.
Yeah.
So if one stabilizes by like all the like Shelton class operators, then somehow the regulators like secondary that goes away. So
that goes away when you stabilize. It goes away. Yes. Okay.
Yeah. So somehow one has to. So it's a it's very subtle. Like yeah, very interesting. Like, yeah.
Yes.
Yeah, I mean, it's a very interesting question, but I don't know the answer.
Mm-hmm.
Do we have more questions? Okay, so let us thank Paolo very much for his wonderful talk.
Thank you. Thank you.
Thank you.
Grazie mille, Paolo.
Okay.
Grazie, Paolo.
Grazie a voi. Okay. Ciao.
See you next week.
See you next week. Yes.